Okay, let's get started. I'm Heiko, and I'm here to talk about Akka Streams. But something terrible has happened. Did you go to Martin's keynote yesterday? Who went? Okay, did you see what happened to his slides? He lost a couple of slides. Very bad. Total disaster. But something even worse happened to me. I lost all my slides. I don't have slides. So let's do some live coding, live demos. Maybe you can help me a little bit, okay? So sometimes when I'm out of ideas, please jump in. And I'm so glad to have Victor here. One of the inventor of this thing here, Reactive Streams. If you don't know what Akka Streams is, make sure you understand Reactive Streams. But let's not read, let's code. Okay. First, a little bit about, about the basics. Akka Streams, of course, is built on top of Akka. So therefore, in order to use the API, we also need to create an active system, and we need to create this strange materializer, which we'll cover later in some detail. And before we start hacking, let's take a look at what we would like to do. So I did prepare something. It's not shown here anyway. Let me just run the application we are going to write for you guys. So this very advanced example of streams. As you can see, it's printing this learn new Akka Streams for great good 7 times, 7 lines, always indented a little bit more, and obviously pretty slowly character by character. That's what we are going to implement now, step by step. Oh no, that's the solution. Let me go back to the initial state. Whew. I hope you didn't see that. All right, here we go. So first, we need to think about how a stream processing topology could look like that behaves like this. In Akka Streams, there is an API to express linear streaming topologies. And this is comprised of mainly 3 building blocks called source, flow, and sink. A source can produce elements, a sink can consume elements, and a flow is the thing in between. Let's start with a source. We have to import the Scala Days L1 because for some reason Scala also has a Java API. And we start with a single element. Let me copy that. A single element. So if we look at the type of this expression, we see that it is a source string. And let's just ignore the not used for the time being. So this source is producing strings. So far, so good. What can we do with it? In order to build a minimal stream that can be run, we need to feed the elements into a sink. So we use the to combinator, and we create a sink dot for each IntelliJ. Let me import that. Okay, for each print ln. Hooray. Let me format that nicely. And now we have a runnable graph of not used. So whenever you combine or connect all the inlets and outlets of the sinks and sources and flows, you get a runnable graph. Nothing is unconnected, and therefore it can be run. And running means to invoke the run method. So until here, before invoking the run method, this here is just a blueprint. It's a cold stream. Nothing is flowing, no elements, nothing is happening. When we call run, we actually run the stream. It becomes hot. The problem with this run method is it takes an implicit materializer, and that's the reason why we had to define it up here. The materializer takes the blueprint and maps it. In this case, it's an actor materializer onto actors, okay? So what do we get as a return value? not used. All right, let's give it a try and, oh, sorry, no breakpoint, and run it. By the way, who is already using Akka Streams? Okay, cool. We will do some more advanced stuff later, no worries. And you can see it's working. Unfortunately, the program is still running. It hasn't terminated, although the stream has completed. And that's because the actor system is still there. It hasn't terminated. We haven't terminated it. So let's try to do that next. It would be nice to know when the stream has completed. And this is when materialized values enter the stage. If we look at this sync for each, we get a sync of string and future of done. So now let's talk about the second type parameter. In Akka Streams, every stage, sync, flow, source, whatever, custom stages, has a materialized value, or it produces a materialized value when you run the stream. And this value lets you interact with the running stream. Some of the stages don't have interesting materialized values, like this source single, it has this materialized value of type not used, and that's like unit. Nothing interesting. But the sync for each tells us or gives us a future of done, so that signals when it has completed. So the question is, why don't we see that? If we look at this, it's a runnable graph of not used, and the not used comes from the source singer. Where have we lost our materialized value of the sync for each? Well, the reason why we lost it is this two combinator. The two combinator just keeps the left materialized value. So maybe we can just do a little trick and use toMat. Oh, sorry. toMat is more or less the same, but we have to specify which materialized values to keep. Now let's keep the right one. If we look at the type now, it's a runnable graph of future of done. Hooray! We could also use keep both, then we would get a tuple, and that way we could keep or get all the materialized values of all the stages in a huge stream. Usually we are just interested in one or two. So if we run that, we get this future, and now we can do .on complete, regardless what it is, failure or normal completion. We go to the system and we terminate it. Hooray, and we should not forget to import the almighty dispatcher. We need that for the future. Here we go. And if we run that again, we will see that the process has exited. Hooray, great. By the way, if you have questions, you can ask them later, because we need the mic, sorry for that. So we are getting close to the solution, right? But source single is just creating a single element. We need more than a single, we need 7. So let's use source repeat. But that creates a real stream, an infinite stream, okay? So we have to limit that to 7. Could you help me with that? Some suggestions? Ah, yeah, thank you. Take, of course. Hooray. Okay, let's give it a try. Yes, great. Next thing we have to do is take care of the indentation, okay? Any ideas how we could do that? Yeah, we could zip with an index or something. So sources or streams can be zipped. Let's zip it up here. Doesn't really matter. Zip, and there's even a zip with index, but we can also zip it with another source, just to show you how we could create a source which produces indices. Like this, okay. And now, if you look at that, we have a source of string, oh, sorry. No, what's wrong? Okay, sure. With a source of string int tuples, okay? With those, we could now use map. Unfortunately, this is not Dotty, so we have to use case. That's the string, and that's the n. And now we can do something wonderful. Say val I equals blank times n. In Scala, you can multiply strings. Isn't that awesome? Now we do s. Sorry, I s. Wonderful string interpolation, almost like a boss. John, are you here? No? Anyway. And yeah, that's it. Cool. So there's only one piece missing, which is we should print character by character. Any idea how we could do that? Sorry? Throttling, yeah, we do that later. Sorry? Yeah, exactly. So we have strings, and we should probably map each string to all its chars. The problem is a string is a single element, chars are multiple elements. So let's see. Yeah, exactly. You know your API. So there's a map concat. Map concat expects a, let me just show it here. Expects a function that takes a string in our case to an iterable of some other type, character in our case. So that's a perfect fit, right? And the cool thing is Scala treats strings as sequences of characters implicitly if necessary, so we even don't have to change anything. Well, except for the fact that we lost the, well, no, let me just do it like this. We have a small problem, which we will see here. So we're printing each character, so we don't do the print ln here, but the print, and now we don't have a line break, so we have to add a line break here using string interpolation with the f string context. And hooray! That was too fast, right? And you already mentioned we should throttle that thing. So this is another nice feature, or another nice API method here. We have the throttle. We can say, okay, we want one element. No, of course, 42 per second. I think I have to import duration int. Exactly. And then we have to say, oh, the maximum burst one, and then throttling mode, shaping. The other one is enforcing, which would then fail the stream if upstream is too fast. I think we are now getting there. Yeah, cool. It's just not printed as nicely here in IntelliJ, but that's it. Thanks for your help, guys. What we have seen here is a simple example of a linear stream processing topology using sources, sinks, and using a couple of these built-in stages like zip, take, map, concat, and so on. Typically, Akka Streams would map each of those stages onto an actor when we are using this actor materializer. But by default, there's an optimization turned on. It's called auto-fusing. So it will fuse all those operations into a single actor. You could either turn off that in the configuration, but I think it's a good default. What you rather should do if you really want to have asynchronous boundaries in your stream, introduce those explicitly like this, by calling async. This would now effectively map this blueprint onto two actors, one for those stages, sorry, and the rest. Okay? One of the design principles of Akka Streams was to make it easy to create parts of stream processing topologies. Makes it easy for you to create sources or sinks or flows and to reuse them. And therefore, Each of those blueprints is immutable and can be freely shared because it's only the blueprint, right? And once you materialize it, the things start happening and elements start flowing. And what we could also do, but I don't do that live now, I will just show you the final solution, is that we could break the graph into reusable parts. So I have split that into several random parts. So this is 7 lines. That's just the source repeat takes 7, so it has the type source of string not used. Here I have defined a flow, and I have taken 7 lines via this flow. So via is another combinator to combine a source and a flow. So that has type string, char not used. So it's a flow that takes strings and as an input and as an output it has chars. And finally, print throttled is a sync. So it's a flow throttle and then to mat with this sync for each. And yeah, we can then reuse those components, or we can reuse them like we did here, but we could reuse it throughout our code base. All right. This is the Flow API. This is the API to define linear stream processing topologies, which is probably what you need in most of the cases, 80%, I don't know. But sometimes you want to write stream topology that is more complicated. And Akka Streams allows you to do that. It has another API, the Graph API. And when you use this Graph API, you can build almost random graphs, even having cycles. So I want to show you that. But before that, I would like to say that even if you use the Flow API, under the hood, everything is represented as a graph. Okay, so this is like, well, the one-shop API for the linear stuff. So the other use case I have for you guys is an access log for a HTTP server written with Akka HTTP. So last week I was at a client and they were asking me, okay, Akka HTTP, that's a HTTP server. Why doesn't it write an access log like Apache? And I said, oh, wait a moment, Akka HTTP is just a library and you can use it to build a HTTP server, but because it's just a library, it doesn't have an access log built in. And I started thinking, and I said, oh, it should be probably pretty easy to implement. Who knows Akka HTTP? Okay, many, almost most. That's great. So for those who don't know, I think it's not terribly complicated to understand what I'm going to show. So in Akka HTTP, you invoke this bind and handle method with an interface and a port for the socket and a route, which is the handler for handling requests. And it's a flow from request to response, okay? So it is defined in this method, in this example here, using directives. Yeah, it's pretty neat, DSL, to define those flows as a route. And the bind and handle method, as I said, expects a handler, which is a flow from request to response. So I started thinking, it should be possible to wrap the handler in a larger flow, which has a step before the request is moved into the handler and a step or a stage which is applied after to all the responses, right? So I came up with that idea here. No, where is it? Oh, it's not the demo, sorry. It's, come on. Here we go. I came up with that idea for a graph, okay? So if you look at that shape of the whole graph, it's a flow because it has an inlet and an outlet. And within that graph, we have a couple of stages. So here we have a broadcast stage, which takes requests and broadcasts the requests to 2 downstream stages. So one goes to the handler of the requests, and from the handler it goes to another broadcast. The other broadcast for the responses emits elements to the outlet of the overall flow, but also to a zip stage. The request goes to another flow which enriches it, so we could add a timestamp or something here, and feeds it to the zip stage too. And then here we have our access log. That's a sink for enriched requests and responses. So in the simplest case, you would just write stuff to a log. Like in this demo here, we want to be able to do route with access log. This is a function enriching the request, so it's tupling up the request with timestamp. And then we say access log, and that's just a sink. It's a sink, as you can see here, which takes the request and timestamp tuples plus the response in another outer tuple and writes, logs the method, the path, the status, and the time in micros. Does that make sense? So the only question is, how can we write that nice graph? Because it's not yet written. And let's try that. So in order to do that, we need to use the graph API. So we create a flow.from graph. That's the API to do that, because we want to have a flow at the end of the day. And here we have to use the graph DSL. We have a create method on it. And we have a create method on it, so here we have our access log. The access log is just a type alias for a sink, which takes the enriched request and the response. So the first thing we need to provide as another argument to the create method is a function that takes a builder. And in this case, we also have to give it back the access log. That's just a detail. I don't want to dive into that. And let's make the compiler happy by adding a couple of question marks. It's always important, I think. So what we should return from that method is the shape. And we want to return a flow shape. Okay, a flow shape has an inlet and an outlet. We don't yet know what they are. But from looking at this picture here, we can already tell that we probably want to add a broadcast stage to that graph. And therefore, let's begin. First, we also have to import the graph DSL implicits. And then we can get started. So yeah, we can still see that. So first, let's add this broadcast request to our graph by using the builder. So the builder is a mutable builder, and it is only mutated as long as, the builder is mutable, but it produces an immutable flow. So it produces a blueprint which can be freely shared again. So we want to add a broadcast. And the broadcast is, if you look here, defined using the apply method. So we have to provide the type of the elements. It's a uniform fan-out shape. It emits the same elements to all its outlets. And we have to define the number. So the type of the elements, that is HTTP request, right? Okay. And we want to have 2 outlets. Great. So we can then already use this broadcast request stage and use its inlet to connect it. So this is the first connection we are drawing, okay? We also have another broadcast response. That was easy. We have our handler and some other stuff. So let's start drawing the graph. The broadcast response can also be used, of course, to connect its outlet. So we have to say broadcast result 0 or 1, doesn't really matter. So to connect it to the flow shape. In order to connect those various stages within the graph, we could use normal methods like add edge. I even don't know the exact names of those methods, but we can use a very nice operator-based syntax. And that's what I'm going to show you now. So if you want to connect the broadcast request with the handler, we can do it the following way. Broadcast request dot out 0 arrow handler, okay? And I think I need an implicit builder here. All right. Okay, cool. So that adds the edge, that adds the connection between the broadcast request stage and the handler stage. As you can probably guess, we can continue from the handler to the broadcast response. So we have already implemented this path here. Cool. Next thing we need to do is enrich request. So that is a flow that applies the given function here from a request to A. So let's add that. Well, enrich request equals builder dot add. Now we need to add a flow taking requests. And we map over F, okay? So the type of this thing is flow shape of HTTP request to A. So what we can do now is we can say, okay, we connect the other outlet of this thing here to our flow. Enrich request. Great. And we finally need the zip stage. Builder.add. We need to add a zip. Zip is not a uniform fan in. It has two types. So I think in this case, depending on how we want to zip it, I think I forgot it. Damn. So let's say the first element is this one here, the A, which comes from the enrich request flow, and the other one is the HTTP response. Okay, great. So once we did that, we can say, okay, we feed that into zip dot in 0. That's the inlet for the A. Great. And then we also need to feed something else into the zip in 1, namely the broadcast response dot out 1. Okay? Because we have already used the out 0 to stream elements to the outlet of the flow shape, so therefore we're connecting the zip this way. Okay. I mean, this looks a little bit like a cycle, so we can see you can use operators in both directions. That's pretty neat. In this case, I wouldn't even do it because it's not a cycle, so it's maybe confusing. So instead, we can do that. But broadcast res is here, so maybe to make it nice, we can put it up there. Do it like this. I don't know. I will later show you a sample solution where everything is very nicely formatted. So I think there's only one thing missing. Yeah, and that is here the access log. We need to connect it to zip. So let's say zip dot out connected to the access log. And that is given up here as a parameter. And hooray, seems to work. Great. Yeah, that's a neat graph that does its job. Just let me show you that it's really working. I better undo my changes and show you the sample solutions as I just said. Okay, so in the sample solution, I have tried to make it look a little nicer to really resemble this drawing. It's not always possible, perfect fashion, but yeah, hopefully I wasn't too bad at that. So you can see from the broadcast request, requests flow to the handler and to enrich request, and from there to the zip, and so on and so on. Okay. So when we run that, oh yeah, maybe I run it in the console. I think that makes more sense. Okay, I'm running it here. Okay, cool listening. So if we send some HTTP requests, we should see the access log up here, method, path, status code, and so on. Great, it's working. And interestingly, I haven't found something like this mini library or micro library in the interwebs so far. So I have created an open source project. You can use it. It's called Accesses, if you think that's useful. It's a micro library, micro all the things, right? That's the whole. That's really the whole code. Okay, cool. So we still have 10 minutes. I would like to show you one more example of an even more powerful graph, because initially I told you that graphs could even have cycles. Don't worry, we don't have to code that ourselves. That would be too hard. I will show you a neat little example. So in Akka HTTP, there is support for server-send events. Who knows server-send events? A couple of you. It's almost like what WebSockets, but only in one direction, from the server to the client. And let me stop that. And oh, start, sorry. Cool. Now we have a server which oh, I don't know the URL, sorry. So we have a server that produces servers and events, okay? And here we have another program which wants to consume those servers and events. And in order to do that, Alpaca, the camel on right version of Akka, has a connector for servers and events, and that's called event source. And that has to be given a URI to connect to the HTTP server to get the source of servers and events, a way to send requests. It can start with a last event ID. It's optional. And here, that's the most important one. It's a reconnect delay in case connections are interrupted or just completed by the server. So if we run this here, we will see the following, hopefully. Oh yeah, okay, cool. So you can see that for each println, we get the service and events. These are case classes. And we start with 43, because the last we told the server we had seen was 42. Perfect number, right? And what you also notice here is that after 10 elements, there's a delay, like 82 here, 3-second delay. So this server is not really giving us a continuous source of events, but it just gives us 10, and then we have to reconnect. And this library does it. And we can even stop the server. And then no more elements are printed down here, of course. We start it again. And this event source client is retrying every 3 seconds, and you can see it continues as soon as the server is up again. So this is quite nice to integrate, or for integration of microservices, for example. And what I would like to show you is how one can implement such an event source which retries to get stuff from the HTTP server. And that is code from the Alpaca project. So again, we write something using the Graph DSL. In this case, it's a source, not a flow. But yeah, it looks very similar to what you have seen before. And here, this is like the essence. We have a graph that, that has a cycle. So you can see that something flows from here to a merge, to another flow, to a broadcast, and from the broadcast it goes to that flow, but also to back in a cycle via that flow to the merge. Or here's even a nice picture, but that's too large. Well, anyway, yeah, almost. So it's a cycle, as you can see here, and nothing special needs to be done, as you can see down there, to implement a graph with a cycle. You just need to connect the various shapes in the way that is necessary. Of course, you need to pay attention to cycles because you can easily produce deadlocks or something, which hopefully is not the case in this graph here. I don't want to dive into the details. If you're interested, just check it out. It's on Alpaca SSE connector. And yeah, that's it. No slides. Sorry for that. Thanks for your help with the coding. And I think we still have a couple of minutes for questions. Hey.
So once this is compiled and you have the nice little drawing up top, from the code, is there enough information in that bytecode to produce the drawing, or is some of that kind of lost at that point?
No, I had to do that drawing manually.
But I know that you did that. But does the in-memory model contain enough detail that you could?
Yeah, probably.
Okay.
I think so.
I have a question regarding the graph you showed regarding the access log. So given the at most once delivery semantics in Akka, I think you might end up zipping wrong requests and wrong requests with wrong answers in the zip operator. How would you go about that?
Oh, that's a very good question. So I don't think it's, as you just mentioned, at least, okay, at least once delivery guarantee. Yeah, that's a good point. But looking at the actual API in question, we are dealing with the bind and handle, which expects a flow from request to response. Now, what I haven't told you is that Akka HTTP materializes a subflow for each connection. So per connection, such a handler is materialized or run. And the HTTP protocol demands, or at least HTTP 1.1 demands, that there is a strict ordering. So what I did here is valid, but this is not valid in general. So if you have a flow, elements which, or let's put it another way, the sequence of elements that flow into that flow need not be the same sequence that flows out of the flow in general. So that could happen in general, but not in the case of HTTP. So if this would happen, it were a bug in Akka HTTP. Thank you. Okay, up there, 2 questions. Jochen?
Yes, I have a question about state in graphs.
Okay.
So I had a problem where I wanted to implement a TCP protocol, which started off with a marker, what kind of message it was, and the payload was of a different size. And I had a really hard time to get that working in a graph. So the general question is, how would you keep state to sort of become different types of flows within a graph? I ended up building a custom stage in the end, but I was curious if there's a smart way to handle these problems.
So using a custom stage is certainly a smart way to handle that problem. I have done that several times. But of course, it's preferable to use the built-in stages if that's enough, or if they well, serve the purpose. So maybe it all depends on how complicated your problem is. So there's a stateful map concat, for example. It's a built-in stage which, well, stateful can accumulate state or keep mutable state. Okay, so maybe give that a try. If that's not enough, write your own graph stage, which is not too hard in my opinion. It's a good API.
All right, thanks.
Welcome.
Just a question about how do you handle two syncs after a broadcast where one sync is becoming significantly slower than the other, and you basically want to make sure that the fast sync is the one that gets the data. So like you start dropping when you're like going beyond 80% of the speed of the other sync, you want to start dropping. So you're not interested that the second sync receives all, it's the best effort, but you really like you have the broadcast. So normally I think like it will result in slowing down the whole graph. Yeah. So, but I want like one sync to be like the primary sync and the secondary sync to be a best effort. And like at the moment when it's dropping down to 50%, start ignoring.
Okay, yeah.
How would you do that?
Okay, so there's various built-in stages which you can use to decouple the speeds of upstream and downstream. So in this case, wow, how's it called? Is it called conflate? Victor, is it called conflate? Oh, he's not paying attention. Okay, let me just check that. So there's a conflate state. Allow a faster upstream to progress independently of a lower. Yeah, that would be one. So you prefix it with that stage that accumulates everything, maybe calculates the Durchschnitt. Average, thank you, or whatever, and then the slow sync can consume the average once it is ready to do that, okay? And there's a couple of others. Okay, so I'm running out of time. I'll be around, so if you're interested to talk about it, just find me somewhere. So I don't want to stand between you and lunch. So thanks for your attention and enjoy the rest of the day.